So this is conceptual chemistry, section 9.6, which is called chemical reactions can be slow or fast. Now, our balanced chemical equations that we've learned how to write, those tell us what reactants we need to react together to form what products. We can calculate the formula masses of the reactants and of the products, and with that we can figure out how many grams of product can be produced from however many grams of reactants we started with. And by knowing the bond energies, which we talked about in the last section, of the reactants and the products, we can even calculate the amount of energy involved, whether energy will be absorbed by the reaction or energy will be released by the reaction. We can use the dispersal of energy to determine whether the reaction is favored or not. Is this a reaction that's likely to be spontaneous, or do we have to do something to cause the reaction to happen? Some reactions are very slow, like iron turning to rust. That's not something that you can, it will take a long time if you want to watch iron turn to rust. You will be sitting there for a long time watching it. And others are very fast, like when you add baking soda to vinegar. That's a very fast reaction. So the speed of a reaction is indicated by its reaction rate. So when we put our reactants together, so here we have a little clock up at the top, and I'm going to click through these slides. You can see we start off with our reactant molecules, and over time, the reactants react together to form our products. And so you can see in this slide that we have our products. One more time, let me slide this over here. We have our reactants, and over time, these reactants react to form our products. So now we only have the products. Okay, so our reaction rate is the speed of the reaction. It tells how quickly the concentration of reactants decreases. It also tells how quickly the concentration of the products increases. The rate of a reaction is going to depend upon the collisions among the molecules. These molecules have to actually hit each other to be able to grab onto each other. Think about it like a game of bumper cars. If the cars miss each other, there's no reaction. They have to actually hit each other to react. Okay. So here you can see two reactant molecules coming together. They have to actually collide in order for the reaction to occur. So increasing the number of collisions will increase the reaction rate. And here you can see a nitrogen molecule and an oxygen molecule, and they are moving closer and closer together until they actually collide, and then they react when they collide and form nitrogen monoxide. And unfortunately, this doesn't actually work. The little video that's supposed to play here, I can't make it work. So increasing the concentration of your reactants will increase the reaction rate because it will increase the number of collisions that occur per second. And that will increase the rate of reaction. So here's just, this is a less concentrated, on the left you see a less concentrated picture, and on the right you see a more concentrated picture. You can tell if there's a whole lot more of the molecules in the same amount of space, collisions are going to happen more frequently. So here we have a gas inside of with a piston on top, and you can see here's a close-up of all the molecules whizzing around. If we decrease the volume, have the same number of molecules in there, then they're going to collide with each other more frequently. So when we increase the volume, that decreases our concentration. It means we have less frequent collisions. When we decrease the volume, that squishes everything into a smaller place, and we have a lot more collisions. So not all collisions, though, are going to lead to producing your product. Just because you manage to get the molecules to collide doesn't mean they're going to actually react. Molecules have to actually collide in the correct orientation. Let me see if I can get that slide up here. Okay, do you see on the right where we have this actual collision taking place, you can see we have two molecules of one type colliding with two molecules of the other type. If this red molecule was at a 90-degree angle to what it is now, if it was rotated, these wouldn't react. They wouldn't be colliding in the correct orientation to be able to grab onto each other's electrons. So they have to actually collide, and they have to collide in the correct orientation in order to be able to produce their reactants. I'm sorry, to produce their products. Reactants are what you react in order to make products. Also, the molecules have to collide with enough energy to be able to break their bonds. If they don't hit hard enough, the reaction isn't going to happen. When the temperature is higher, their energy is higher. Kinetic energy is related to speed, and that's related to the temperature. So reactions are going to be a lot more likely to occur. So at ambient temperatures, that's room temperatures, nitrogen and oxygen molecules don't have enough energy to form nitrogen monoxide. So where is it that we might have this reaction occur? Well, this picture gives you an idea. The heat of a lightning bolt dramatically increases the kinetic energy of nearby molecules so that the nitrogen molecules and oxygen molecules that collide near this lightning bolt are going to have enough energy to grab onto each other and become nitrogen monoxide. And then the nitrogen monoxide undergoes further reactions to become the nitrates that are needed by plants for nitrogen fixation that you might have read about in biology. So kinetic energy to break bonds can also come from absorbing electromagnetic radiation, like from sunlight. So nitrogen dioxide can react with sunlight to form nitrogen monoxide and oxygen. Here are some other places where there's enough heat for this type of reaction. Inside of a car engine, in the exhaust coming out from the car is also another place where this can occur. So the activation energy is the minimum energy required to overcome the initial breaking of the bonds in the reactants. If you remember our reaction curve, the activation energy is the energy we need to break the bonds, to break the hold that the nitrogen atoms have on each other, or the hold that the oxygen atoms have on each other. They have to release that bond and then grab onto a different atom. And the amount of energy it takes to break those bonds, that's what we call the activation energy. That's the minimum energy required to break the bonds. And remember, we have that in a bond energy chart that's in the textbook. So our reactants have to be moving fast enough, have sufficient kinetic energy to overcome the energy of activation. These molecules right here are moving fast enough because they have a bigger blur here. They're moving fast enough that they have enough energy to overcome the activation energy and break their bonds. This pair over here you see on the left, they don't have enough energy to overcome the energy barrier. You can see they have a much smaller blur. They're not moving as fast. So if your kinetic energy is less than the activation energy, then no reaction will occur. If the kinetic energy is greater than the activation energy, then the reaction will occur if they actually collide in the correct orientation. As you increase your temperature, you will increase your kinetic energy, so more of the reactant molecules can react. And so this last part is about alligators. They have problems in Florida with, in the morning, alligators just getting up and wandering around the road. Why was the alligator lying in the road during the night? Did he just want to be in line? Did he want to meditate on the meaning of life? Or was it because during the night, the road was still dispersing energy? The road is getting heated up during the day, and during the night, it releases that energy. So the alligator can lie on the road and absorb the heat from the road. So that's it for this section. This was chapter 9, section 6, and that is all.